Okay, let's go and go through our content for today. We've been talking about inter-process communication quite a bit. And so what we're going to talk about today is inter-process communication on something that's more of a distributed system, just rather than just a single system. And so first off, let's kind of go through and talk about what we're talking about here. So the first thing is we've been communicating between processes. So process, remember, is kind of stuck in its own little box. It has its own memory, has its own process space. It might even run on a separate processor from another process. It could run on the same one and just switch between them rapidly, like with the thread, but they are kind of isolated in their own process space. And so we've looked at ways of communicating between those using queues, using pipes, using kind of these shared memory value array objects, using something a little higher level with a manager object, and then using kind of these shared memory blocks directly that we could access by name. And each of those had its own advantages and disadvantages, but all of them have one major problem, one shortcoming. And that shortcoming is that we're really talking about processes that are running all in one single computer system on the same operating system on the same machine. And that means that makes them really kind of unsuitable for kind of this distributed system model where we have a cluster of machines that we all want to work on a problem together, or we have a cloud-based system with an array of dozens and dozens of processors that we want to be able to activate to work on large problems or work on something to get it done more quickly. So think about something like Google. When you do a search, there's not one computer system that's responsible for coming up with the search results. It's across this kind of cluster of machines that all work together to come up with the answer to your search query. And that's the kind of thing that we want to look at. How do we get those kinds of systems to communicate with each other? Now, another way to think about that is all of the methods that we talked about previously allow a process on one system to exchange data with, or they don't allow us to have a process on one system to exchange data with processes on another system. So they're all kind of stuck in their own process space with their own memory, and they can communicate between those, but we don't have any way to get out of that single computer system right now. Now, we're going to need some kind of different method in order to allow us to do that. And so what we're going to look at today is a couple of the standard methods. We're going to look at sockets. We're also going to look at these multiprocessing connection objects, which is kind of a simplified version of something that sits on top of sockets where we don't it could also sit on top of like a named pipe or something. It doesn't really matter to us. We're just going to open them. We're going to talk between the two things. And we're going to use them. Now, there are a lot of other options available too. MPI, which is kind of an industry standard way of having distributed systems talk to each other. There used to be some other things like PVM, a parallel virtual machine architecture that was around. But for Python, there's also Pyro4, which is a remote object library that allows you to create objects that kind of exist on another machine that you can access remotely, call methods, get returned results, change the data. It gets changed in kind of the distributed form of that. That can be useful. And there's another kind of powerful module called Ray, which kind of has a whole lot of distributed data features built into that. And there's some other ones as well. Now, we're going to start off with sockets. We're actually going to start off with these two standard ones, sockets and then the connection objects. That's what we're going to do today. All right, so looking at sockets. Sockets are really one of the most widely used methodologies there is. The entire internet is built on top of sockets, but then other systems take advantage of sockets as well. So sockets is kind of like a network library, and we can use that to write code that talks from one machine to another machine in kind of the standardized way. And the other thing about sockets is they support both kind of stream-based kind of protocols as well as datagrams. In other words, stream-based protocols, you make a connection between two machines, you keep the connection open, kind of like a phone call. Data can go in, data can come out, you can write, you can read while the connection is open. And it'll, behind the scenes, handle the reliability of that stream, even though behind the scenes it's datagram based. Or we could write in datagrams directly where we say, kind of like a postal system, here's a letter, send it, here's another letter, send it. And datagram based communication is not reliable, but it can be much faster and have much lower overhead and latency than a stream-based system. Sockets allows us to do either one or the other or both of those. Your web browser is built using sockets. When you're watching YouTube and streaming a video, that has sockets. Essentially, sockets are the technology that connects everything together on the internet. Now, socket programming, that's what we're interested in here. That you can think of a socket as when you open a socket, you're creating a connection to the networking system of the machine. And even if your network has multiple kind of subsystems in it, you can connect to whichever one you want using the same kind of connection methodology using a socket. So you'll notice here, before we do anything else, we have to create that connection to the underlying architecture. And the first part of that is creating this socket. And when we create a socket, there are two parameters. This is AF_INET, which AF stands for address family. I suppose you could think of it as something else, but it's address family. And the address family for the internet is the first one we're picking there. And then sock_stream means it's going to be a connection-oriented protocol, or in this case, a TCP stream connection. And that TCP stream connection is what's going to make a connection that's going to be guaranteed to be reliable. Now, once we have that socket created, then we can use it to connect to some other process somewhere. So notice that to connect on this end, I'm basically say connect to this address and that port number. And the port numbers you can think of kind of like a phone extension, or it has to be where some other process is listening for a connection to come in. And this is the machine. Now this could be the same machine we're already on. We could use our machine, localhost, or 127.0.0.1, which is the number for localhost. So it could be on our machine, or this could be somewhere else on the internet. And the port number, the only restriction on that is that has to be an open port on that machine upon which the other end of the connection is listening to that for somebody to connect to that. All right, so pretty simple. We create a socket. We use the socket to connect to whatever address and whatever port we want to. Now, for that to work, there has to be a server listening on the other end on that particular machine that we specify and on that port. And that, essentially in the terminology we're using here, the listening machine we're going to call a server. The connecting machine we're going to call a client. And a client is the one doing the connecting. If you think about it in phone call terms, the server would be somebody waiting for the phone to ring. The client would be somebody who's dialing the phone up. So don't think of server like in this case, as a big box that has computer equipment in it that is serving web pages. Think of it as, although web servers are really listening on a socket waiting for a connection, but think of it more as just the concept of the server is the one waiting for the call to come in, and the client is the one making the call. Okay. Oops. So let's look at the server code, the kind of listener code. It's a little more complex. So we have to create a socket. That's the same as we did on the other end. And now we have to do something called bind, where we bind that server socket that we created. We have to bind it to an address. So a lot of machines, like my laptop, for example, has a wired Ethernet connection. It also has a wireless Ethernet connection. And I could have both of those active at one time. So I have to essentially bind to whichever one I want. So binding that says tie this socket into this piece of network hardware on a particular port. So in this case, I'm using socket that gets host name. This is get my own local host name directly from that, and bind to port 80. Now, after I've bound to that port, I'm not quite ready to receive connections yet. I have to call this server socket.listen to essentially, that's like telling a person, hey, listen for that phone to ring. The number in parentheses here, we're not going to spend a lot of time talking about that right now, but that's called the backlog. That's how many connections this socket can kind of queue up and have waiting simultaneously. So it's kind of like a rollover line on a telephone, that it won't ring busy as long as not more than 5 people are trying to connect at one time. So that backlog, we could change the number. We make it 1 if we only want to accept one connection at a time. We can make it 5 so they can be 5. And that's not really active connections necessarily. That's how many you're waiting in the backlog to be handled. Okay, so now that we're listening, we can so we're listening to the phone to ring. Now when it rings, we have to do something about that. So the way that we're going to do that is with this accept call. So same socket.accept. That will block and wait for a connection to come in. And when a connection comes in, it returns to us a new socket that we're going to talk to that person on, and it returns the address of who connected to us. So we can see the address of who it is that's connecting to us, and we get a socket to talk to them through. So in other words, when the phone rings, we pick up the line. We have this new kind of connection now that we're going to talk. So we're not going to talk over the server socket. It's kind of reserved for listening and accepting connections. When a connection is accepted, think of it as rolling over to the main phone line rings. It rolls over to some new extension to be answered so the main phone line can be freed up to continue receiving incoming calls. All right, the last couple things here is now that we're connected. At this point, if we get past this accept, we are connected to that machine on the other end. So once we're connected, we can send data through that connection. We can receive data from that connection, and that's guaranteed to be reliable. So if we send something and it says that it worked, we know that it sent it. If we receive data, we know that it hasn't been corrupted in some way. We know the data is correct. And then when we're done with communicating, we can close the socket. Okay, so one thing to note is that for that to work, one of the machines has to be listening, has to be a server. The other one has to be a client. So that means when we're designing a distributed system that uses sockets, we have to plan out where's the server in our architecture, where's the client, and they could both actually be listening and connecting if you want, just like a phone. If I want to make a phone call, I could use the phone. If the phone call comes in, I can answer the call. So I could set up one, and I could actually have more than one socket to it. I could set up one socket for listening, one socket for sending and connecting. And so really you could, but you have to think about that in your architecture. That we have to, it's not like a shared memory where just everybody writes to it and reads from it and accesses it at the same time. We have to have, take into account the communication mechanism itself. Now, the one thing to note is the server can handle multiple client connections. So you could have a server, just like a web server, that serves the same web page or different web pages to different people as they connect to it. That's totally fine. Now, this little chart over here kind of shows the sequence of here's the client, here's the server. So the client gets a socket, it binds to the socket, it listens on the socket, and then it accepts. So this will block until the accept happens. On the other end, the client end, it gets a socket, it connects, and that connect, now this connect and this accept kind of line up with each other. And so as soon as that we get past the accept and this connect, we know we're now connected. So now that we're connected, we can write, the other end will read, and really it's, in our case, it's send and receive. So we can send data that will be received. They can then send a response back using send. We can receive the response. And once that connection is open, we can do that as many times as we want. We can exchange as much data. But when we're done with that, we can actually close, and that there's an end of file notification that goes over here, and this end can close. So we don't need to wait for the CUF notification. We can just have this close when we know we're done. But the idea is that that's the sequence we're going to do. This is the server side. This is the client side. Okay, so here's a complete example that if you put it in and run this, it'll work. And notice that in this case, I didn't use a remote server name. I used this 127.0.1 as the local host, meaning your own machine. But if I run this in one process and this in another process, they will communicate information between them. In this case, the information that I'm sending is just kind of this hello. And notice because the way Python 3 works, Python 3 has this, the strings are all Unicode strings by default. And so if I want to encode that in kind of an 8-bit byte string, like a traditional string, I have to do this .encode Latin thing. I have no idea why it's Latin that we encoded in, but why that the default 8-bit byte version of that is called Latin, but it's the Latin character set. So basically we have to encode that. And then on the other end, when I read that in, I decode it. I can decode it back from Latin to get back the Unicode string or the string that was sent originally. So if you run this, the client will connect. It'll receive some data. Notice that that's the maximum amount of data that I'm allowing it to receive at any given time. That doesn't mean I'm going to get that much data. That's just saying that's the limit on how much I want to ever receive at once. And you could set that to other things if you knew the size of the message you were expecting. But I receive that data. It comes in here, I decode it, and I print it. So I'm going to have hello exclamation mark printed that was sent to me from the other end. Now, one thing to note is that the send and receive here are basically sending kind of this byte array. They're just sending this array of bytes through the socket, and it's coming in on this side and then receiving it on the other side. Now, a couple of notes about that they both work on kind of a data stream. Both send and receive work on this data stream. So when you say send, if you have a really large amount of data, the send will return the amount of data that it actually successfully sent, which might not be the whole message. So if you say send this 4 meg block of data, then it might say that function send might return, but it'll return to you how much of it actually sent so far. So if you want to send a large amount of data, it's up to you to create a while loop around that says send. Let's say there was 4 megabytes of data. Send, it might say, okay, I sent like 10K of that. And then you would call send again to send the next 10K and the next 10K. So you'd have to build a loop that kind of goes through the data, sending it in chunks if send didn't send all of it at once. But if it says it sent, let's say, 5K of that data, we know that that was successful. If it wasn't all of the data we meant to send, we have to call send again, starting with the next group of the data there. So we might have to call send multiple times. The same thing is true on receive. When receive kind of returns a block of data, it might not be the whole message it was intended for us. It might be part of it. So receive might have to be called again and again until we get all of the data we were expecting. Now, how do we know how much data to expect? How do we know how many times we have to call it? We're going to have to create some kind of protocol that does that for us. And the reason that it does that way is that TCP does guarantee this reliable transfer. When send or receive returns that number of bytes, we know that that number was received correctly. We know it was sent correctly. But because they don't want to lock up the network for a really long time, they basically designed it so it'll send what it can, return for a little bit, send some more later, return for a little bit. And so the idea behind why it was set up the way it was, it doesn't know when the end of our data is. It just considers it a stream. So as we start feeding data into the stream, it might send what it can, but it then is going to come back. It's up to us to keep feeding that stream, and it doesn't know where one unit starts and one unit ends. We have to build that into our protocol ourselves. Okay, final details with sockets. Note that a server that creates a socket to talk to the connecting client, that new socket that gets created there leaves the original one open to accept other connections. And that accepting of other connections can be useful because we could actually spawn a thread to handle those incoming connections, which is essentially what web servers do. So in other words, when you say, hey, give me this web page, it doesn't prevent other people from connecting to it at the same time. It basically just says, this person's connected on, they have their new socket that they're going to talk over. I'm going to spin that off into a client. And you'll notice down here I have a little bit of example of how that might work. Is that here's the while loop, here's an accept. When an accept comes in, we create a thread, server thread, and then I don't have the code in here for how the server thread would work. But the server thread, we pass that new connection socket to it to do the communication on, and we also could pass the address in there. Actually, this should probably say client address here. But the idea here, that client address that gets passed in there on the client socket, that can spawn that off into a new thread that we then start to talk on that one, which frees this up to immediately go back to the top and accept another one. So you can actually have multiple connections going at one time. Okay, now, one of the things that comes up, though, is like if this is just a stream of kind of binary data or a stream of bytes that we're pushing into these sockets and pulling out of the sockets with send and receive, that can create a little bit of a problem. If we want to send an actual object through that list, or like a list or a dictionary or even a string from one end to the other end, we have to encode it in some way. In other words, that it's up to us to encode that into a byte array or stream of bytes to be sent, and then on the other end, we have to pull it back out of that byte array back into kind of whatever object form we want. Now, there are a number of options for dealing with this, and I've listed some of them here. Like binary format, you could use pack and unpack, or a binary array using kind of the array module. So you could do that more directly using one of those kind of binary formatting methods. Or to make it a little more readable and understandable, you could use something like JSON, which is JavaScript object notation. And it has this, that's become kind of a standard way of exchanging information on the web. Since JavaScript is in most browsers, JSON is kind of this method of encoding data to be sent across from one end to the other. Python has its own serialization module built in called pickle. It is not as widely used as JSON. There are also things like XML, which is kind of like a hierarchical tag structure for storing data that's used extensively. And then there's one that I actually have used on some projects that I've worked on called msgpack. And the thing I like msgpack is it's a little more compact. It's a binary format, but it is machine independent, and so it's cross-platform, cross-language, and it supports multiple languages. Where pickle is the specific one for Python, JSON is for JavaScript, but also support another language. msgpack was designed to be very compact, a very short representation of the data that we're trying to send. At the same time, it's very fast, and it works with multiple languages. So you could write, for example, a C language server and have it talk to a Python client. You could write a Python language server and have it talk to a Fortran client that connects to it, or C++ or Java. And so msgpack is kind of language independent, machine independent, and it's also fast and compact. So that's actually a pretty good one to look at. And then we could write our own if we want to. We could write our own kind of formatting to put stuff in however we want to, encode it, decode it in whatever way we want to. Now, a couple quick things about those, and then I'll switch off of this for just a second, and I'll look at some examples of what we're talking about with this in Python. But JSON, pickle, and msgpack, even though those work differently behind the scenes, the way we access them is very similar. So if you look at those three different modules, they encode the information in a totally different way, but they were designed to be very similar as far as how you access them to the module. They have two kind of methods that are of interest to us. One is dumps, which stands for dump string. And what that does is it takes some object, so we pass an object into it, it converts it into a serialized kind of byte array string that it pushes out over here. Now loads does the opposite. We pass the string into it, and it returns to us that object that it created. And that works for most basic data types and container types like lists and dictionaries. And pickle actually will work on arbitrary kind of Python objects as well. The arbitrary Python objects, though, have to be pickleable, meaning they can't have binary subparts to them, or we'll have to convert those parts separately. But essentially, to use that, we basically say serialized data equal json.dumps, and then put some object in there. And you'll note that that's kind of the same for all of these. All of them kind of work in the same way, that basically they all have this dumps method. They all have a loads method. So dumps pass an object in that is serializable. This gives us the buffer, or we pass the buffer in, it gives us the object back. So the idea is that there are some restrictions on that, but in general, it's going to allow us to take an object, serialize it, send it over a socket, deserialize it, and then have that show up. So in other words, we have this process like this. The sender wants to send some data. It serializes it with one of those modules, sticks that into the socket using send that goes through the internet. I should probably have a cloud here to show the internet, because for whatever reason, the cloud is always the internet. And then that comes out the other end and gets received on the receiving machine. When that's received, it gets deserialized, and now we have the object. So it's like the object went from one process to another process across this socket in some way. Now, those sender and receiver can really be anywhere. They could be on the same machine. It could be on different machines on the cluster. It could be on remote machines on the other side of the world. And that one of the things that I've left off is send and receive, remember, can be imperfect. So if you have a really large object, it might get divided up into multiple sends. You have to have multiple receive. We would have to build in some of the logic to do that. It's also important to understand that serialization and deserialization are two additional steps in getting the data from one process to another one. And that has some overhead associated with it, whether we're using pack directly or msgpack, which is pretty fast, or pickle or JSON. It does have overhead no matter what. It takes some processing time to convert that into those buffers to be sent. Whereas if we're on the same machine, we're using shared memory, we don't have that overhead because we're not really serializing, deserializing, sending data, although we could use serialization and deserialization and push things into shared memory as well if we wanted to. All right, let's take a quick look at some of those modules. So let me actually fire up a Python shell here. All right, so I'm going to load a Python shell. And then let me switch over to that so you can see it. Okay, so here's a Python shell. And so what I'm going to do quickly here, if you want to use JSON, just import JSON. If you want to use pickle, import pickle. If you want to use msgpack, you'd have to use pip to install it. But you can import that as well. So importing all those is the same. Now let's say we have something that we want to send across the network. Let me just make it like a list. So I'll call it my list equal. And then inside of here, player 1, player 2. And let me put some other data in here as well. Let me put something like that in there. All right, so I have a list. Now, if I want to take that list, player 1, player 2, and then that tuple, I'll just say that's a color that I've put into there. And I want to decode that. And maybe let's make this list a little more complicated. Let's say this list has maybe the players and their scores. Let me put a score in there. Player 1 has 10. Player 2 has 30. And the time remaining in the game is 100 seconds. And the current color is red in this case. All right, so there's my list. And now if I want to kind of serialize that, notice that if I just say my list here, that has all of that data in there, and it's showing it as a string, but behind the scenes, these are kind of objects. There's a string object and a number object and a string object, a number object and a number object and a tuple. So, but if we want to encode that, I can use JSON.dumps, and I can pass into that my list. But I'm going to need to, that's going to produce this byte array or this string. So I'm going to say message equal. I'm going to do that. Now let's look at what's in message. And you'll notice that it has kind of this JSON representation of that is not really just it printing it out. It's a string that has that. And it's kind of encoded that. Here's a list. And it's got a string and a number and a string and a number and that and this. And just to show this, let's say message 2 equal pickle dot dumps my list. So the same list. Let's look at what that looks like. Notice that's a completely different format that it has. And notice that those that byte array /x80 is just character 80, character 3, kind of that closed bracket q, character 0. So this is all kind of its own representation. The same thing with message packs. If I say message 2 dot or message 3 dot or equal message pack dot dumps, and we called this my list. We look at what message 3 looks like. You'll notice it's a more compact version of something like pickle, what pickle came up with. And actually, to look at the length of those, let's look at the length of each one. So length of message. Okay, so JSON took 48 bytes. If I look at the length of message 2, took 51, so it took a little more for pickle to do it. If I look at the length of msgpack, that's not right, length of message 3, we get 25. So notice that the msgpack was about half of the size of the other two. And again, it's cross-platform, compact, and it's fast, which is why I use it. Now, the whole idea of this, though, is like, what do we do with these? Let me move this up so we can see the bottom here. What do we do with these? So now that we have this string, for example, message. So message looked like that. But if I want to turn that back into this list object, so I'll say new list equal, and I'm going to use JSON again. So JSON dot, I'm going to use loads instead of dumps. And in this case, I put that byte array in there. And now if I look at new list, notice it has back to having those things. Now there is one difference here, that JSON has no way to distinguish between a tuple and a list. So it pulls that back like that. Let's look at what happens when we use pickle for that. So new list 2 equal pickle.loads. But you notice all these work the same. Message 2. And let's look at that. New list 2. You notice that pickle can distinguish between tuples and lists. But you'll notice I get the same data back in the same places. And just for fun, let's look at msgpack. So new list 3 equal msgpack dot loads message 3, new list 3, and there we have. And again, msgpack, kind of same result as from JSON. That all of these are viable alternatives to use. Like I said, I've used both pickle and msgpack and JSON, depends on the project. The disadvantage of pickle is that it's Python specific. msgpack is cross-platform, but the advantage of pickle, it's built in if you're using Python, so very easy. All right, now let's switch back to the presentation here. All right, so back to that presentation. And one of the things about this, we've looked at those serialization modules, and one of the things to note is that there are some complexities there. And the complexities involved there are that we have to do the serialization and deserialization ourselves. The second complexity is the send and receive. When we say send and give it a bunch of data, it might not send all of it. We have to build our own kind of class to make sure it all gets sent. And on the receive end, we need to make sure it all gets received. So you usually end up creating some kind of class that sends the size first and then the buffer of data. And on the receive end, since it got the size first, it knows how much data is to follow. When it gets up to that amount, then it releases the data to be processed. But we have to build our own classes to do that. Now, there is a simpler approach to that that's built for us inside of the multiprocessing module, which we've been using throughout the semester. And the cool thing about this is it kind of handles a lot of the complexity of that for us. The send and receive, it kind of does that. It also handles the serialization and deserialization, so we don't have to worry about it. So the connection object allows us to send and receive kind of objects as long as they're pickleable. And we could send strings, we could send numbers, we could send lists, we could send tuples, we could send lists of lists, you could send lists of dictionaries of lists, whatever we want, we can send. So that can be thought of as kind of this message-oriented connected sockets. So it's sockets that are handling the sending and receiving of those messages in their entirety without us having to worry about it. And it's serializing and deserializing those for us. So it's already done for us in this case. All right, so we've seen connection objects before with pipe. So those are going to look familiar. So let's take a look at those. So the methods for a connection object: send, receive. Send, you put an object in, and on the other end of the connection, receive is going to have that object pop out. Close when we're done with it. Poll can tell whether there's any data to be read, whether there's an object in there or not, ready to do something. So in other words, rather than calling receive and blocking, we could call poll, and it would say either yes, there's something there, or no, there's not. You can also add a timeout there to say, hey, wait for this amount of time before telling me that it is something there or is not. If you leave that blank and just say poll without the timeout in there, it'll immediately return an answer whether yes, there's something in there or no, there's not. Now, there's a few other connection object methods that we're not going to talk about right now, but file number, send bytes, receive bytes, and receive bytes into. Those can be send bytes and receive bytes are not sending objects. Back to this one, though, send, you pass an object into it, and it serializes and sends it, and receives that serialized object and deserializes it. So send and receive are kind of higher level. If we want access to sending in byte arrays ourselves, we can use send bytes and receive bytes to do that, something lower level with these. All right, now the connection objects kind of come with a way to deal with the sockets of those directly as well. So we don't have to create our own socket and do anything with it. It gives us two classes that help with that, a listener class and a client class. So the listener essentially is the server side of things. It waits for a connection to come in, and then when a connection gets created, then it can communicate on it. The client class is the one that's actually doing the connecting to the server. It's acting as a client. And so it's going to connect, and once the connection is made, we can send and receive objects through that connection object. Now, again, you'll need one of each on each end to do that, but remember, one listener could actually talk to more than one client. And the client could talk to one listener, disconnect, talk to a different listener, disconnect. So you can really have some flexible options here. Let's look at some example code that creates these. So the listener example up there, essentially very simple. The only thing we're importing in this case is multiprocessing.connection. That's a submodule of multiprocessing. So we're importing that. Notice I don't have to import socket. I don't have to import anything else, just this. And this, since multiprocessing is a standard module in Python, we don't have to download anything and install anything. We just have that. Now, just like with sockets, we have to set up an address. And I used localhost again, and this made up port number 1234. Now, one of the other things that's cool about the multiprocessing module's connection object, it has built-in authentication. So you can put like a password in here. If you leave auth key blank or leave that off, it won't use authentication. But if I put that there, it'll authenticate the connection so you don't have rogue processes or rogue things on the internet trying to talk to your listener and screwing things up for you. So in a distributed model where you have computers spread out across a cluster of the internet, that can become important, and the connection object handles that for us. And I just put a password in here of secret. Notice that B at the front, that makes this a byte array, which is what this is expecting this to be. So I made a byte array that says secret, and I'm passing in the address and the auth key to this listener. So once this is done, this is going to return a listener object. And that listener object now is what can accept connections. Notice how thinly this is wrapped around sockets. It's very similar. It's just this is creating the socket for us. Listener.accept is waiting for an accepted connection on the socket. Once the connection has been accepted, then we can receive data. Now, this is a little bit different than the send and receive from the socket. This receive is guaranteed that when they said send this whole thing, the whole thing will come through in the receive, and it'll come through and be deserialized back into an object. And in this case, what I did is after I receive that data, I go ahead and close the connection and go back to waiting for another connection. So in other words, the server is going to be connected to, it's going to receive some player data, it's going to disconnect, and then go back to waiting for another connection. On the other end, the data that I passed in is this dictionary. I made a dictionary that has the name of the player, has their X coordinate, their Y coordinate, their health, their speed, and their angle of travel or their heading in the world. So that player data that I'm passing in there, just a single dictionary that I'm passing in, same address and port number, but on the connection, the client end, rather than listening and waiting to accept, I basically just call this connection, pass the address, pass the authentication key in, and then once I'm connected, I get a connection object, and I can do send. This send then sends the object through here, so this player data I essentially have passed this variable here across the network, and now the variable has cloned itself or been duplicated on the other end. So this now has that dictionary, and then up here I just print it out so you can see that happens. So let's quickly look at the output of those. So the output, the listener's waiting for a connection. When this one gets run, it connects. I can tell who I got connected from. And then on the other, I receive the data from this end, and there's the dictionary just like it was on the sending end, and then they both disconnect. So very simple, very small amount of code to do that. And one object has now transported itself from one process into another process by going through that connection object. Similar to what we did with pipes. All right, those listeners and clients, that kind of greatly simplifies the exchange of data between two processes that we would have with sockets. But it does have its own overhead, and it uses pickle behind the scenes rather than some other serialization method. So that could be used with two processes on the same machine. They could be on different machines. They could be in different parts of the world. They could be in the same room together in the same cluster. But it's handling a lot of the serialization and deserialization for us. The next part there is that kind of requires it to be pickleable data when we use send and receive. So objects that can't be pickled, we have to convert them into buffers ourselves or into a string ourselves, and then send that string. So we would have to do that ourselves if it's something that can't be pickled. So something that couldn't be a pickle would be like if you think of a Pygame surface, it has a kind of a binary aspect to it that's not stored in Python directly. It's stored in some C language library that's wrapped, has Pygame wrapped around it, Pygame surface object wrapped around it. That can't be easily pickleable, but you could convert that into a buffer and send the buffer, receive the buffer, and convert it back and have pictures crossing the network relatively easily. But we'd have to do a little more work ourselves. Now, the other thing is if you want to use one of the other methods like JSON or msgpack, you could still do that and then send that as a string object or send it with send buffer and receive buffer. And then we would still end up simplifying the use of sockets to do that. So we can still use those other methods if we want. We would just have to call it ourselves. All right, kind of to finish up here, there are some other objects for doing this as well for distributed computing that are worth mentioning. We mentioned them up front at the very beginning. MPI is a kind of industry standard way to pass messages from one machine to another machine. We might look at that later this semester. Pyro is another useful one. Pyro is kind of a remote object library that allows you to create an object and say, hey, this object is going to be remotely accessible. And the Pyro module will handle method calls coming in, attribute changes coming in, sending those data changes back out to other modules. Ray is another one, relatively new player in the game, but it has a lot of really cool applications for distributed environment. So if you're making a distributed web app where you have a lot of data, like a web search or something like that, Ray might be a useful thing there. It has much lower overhead than some of the other options. It's not cross-language compatible like MPI, but it's a very powerful distributed application development, data sharing thing. And others, you can make your own if you wanted to. All right. So that's all for today. So we'll go ahead and stop there. I would encourage you to play around with that connection object. We are going to have a lab doing that next class. But go ahead and play around with that. We may have have a quiz on some of this stuff as well. It's been a while since we've had a quiz or an assignment directly with some of the stuff that we've been doing. So go ahead and stay safe, and I will talk to you next time.